Thank you for the nice introduction. Thanks to all for coming. What I want to do is try to give you an overview of my field of research, which is cosmological simulations, and in particular cosmological simulation of galaxy formation. And what I want to give is to give a description of the challenges that we have to overcome to carry out these large-scale calculations. And then I will pass to what is the state of the art today in this type of calculations. And in the last part of the talk, I want to explore some future direction in which this cosmological simulation might be going in the near future and in the next, let's say, 5 to 10 years. So let's set the stage. And the task that we have to accomplish with cosmological simulation is quite ambitious. What we want to do is to simulate the evolution of the universe from the beginning, from the Big Bang, almost from the Big Bang, from the cosmic microwave background from which we get our initial conditions. And then we follow all the evolution of the universe till today by solving in some way the equation of physics that govern the evolution of the universe. And at the end we get with a virtual universe on our supercomputers, and we compare those virtual universe to the observational constraint that we have at the current time or even at earlier periods of time. We can repeat this path in several ways, and we end up with a collection of virtual universes. And our hope is that we are able to create in the end a realistic universe, a universe that looks like what we see in observation nowadays, in order to understand how the universe evolves, and especially structure in the universe such as galaxies form and evolve. So to do that, we need a set of initial conditions, and these initial conditions we are quite lucky because we have observation of the cosmic microwave background. In this picture you see the temperature distribution of this radiation, or better, the temperature differences with respect to the average temperature of this radiation. The cosmic microwave background has been emitted 400,000 years after the Big Bang, and as such it brings the imprint of the physical condition of the universe at that period of time. And in particular, since at that time both the matter and radiation were tightly coupled, the differences in temperature are really differences in density of the matter, in the clustering of the matter. I want to emphasize that at this early time, those differences are really tiny. But it is from these tiny seeds that the structure that populate our universe form and evolve. And actually, this observation gives us the most precise initial condition that we can desire in order to start our calculation. From studying the distribution, the angular distribution of this radiation and the properties of this radiation, we have formalized what is known as the standard cosmological models. That is the model that I've been using in these calculations. The key point here is that thanks to observation of the cosmic microwave background, we can know very precisely what is the composition of the universe, what is the energy budget of the universe. And the general consensus is that a large part of the energy budget of the universe is dominated by dark energy. We don't have a clear idea of what this is. We only know that it is responsible for the accelerated expansion of the universe at the present time. And the rest is composed by matter. Again, here the vast majority of the matter is in a component that we call dark matter, and which in the simplest model it interacts solely gravitationally. And dark matter is very important because it forms the backbone on which the structures are formed. It gives us the gravitational potential well, and at the center of which we can form galaxies. And then a tiny fraction of this budget is formed by the so-called baryons. Baryons are everything. It's the ordinary matter of which we are made of. It's a tiny fraction of the budget, but it's extremely important to model the baryonic physics well, because we actually gather almost all of our observational information about the physical condition in the universe by studying baryons. It's essential to model them, but they are very difficult to model because the interaction that they feel is not only gravity. There are a lot of physical processes that can shape the evolution of baryons. And this is where all the problems in modeling the formation and evolution of structure in the universe start. So the key point is that they are a tiny amount, but they are necessary to model them in a very accurate way to get realistic universes. So just to recap, that's what is our task. So we start from the Big Bang, actually from very high redshift, where we have the initial conditions that are given us thanks to the observation of cosmic microwave background. And then we try to follow 14 billion years of evolution until we form galaxies as we see today. This is a beautiful image of M31, the Andromeda galaxy. And from this tiny seed for structure formation, we have to get to the structure that populate the universe nowadays. And this is an incredibly complex process to model, mostly because it's highly nonlinear. We start from a linear theory, but then these galaxies reach well beyond into the nonlinear regime, and all nonlinear processes, as we all know, are very difficult to model. So the key question is, how do we model it? How do we model these 14 billion years of cosmic evolution? And here is when a supercomputer comes to the rescue. So many of the results that I'm going to present today have been possible just because the computing power that we have at our disposal is huge and is constantly increasing. Here in this slide I show you some supercomputing system that I've used in my research work, in my calculation, both in the US and in Europe. And I've mostly used supercomputing resources in Europe just because it's a little bit easier to get big allocation chunk for computing time. Especially in Germany, the situation is like paradise because they have at least 5 or 6 big supercomputing centers, and they have plenty of CPU hours to give us to experiment with our calculation. As I've said, most of the progress that have been made in this field is because the computing power that we have at our disposal is constantly increasing. And here in this plot I show a representation of the so-called Moore's law, which relates the performance of this machine expressed as in number of operations that can be done by this machine per second as a function of time, as a function of year of installation. And in particular, in these 3 lines, I'm showing you on the top line the combined computing power that is available in the top 500 supercomputers in the world. The line that comes immediately after is the number 1 supercomputing system that is currently installed. And the bottom line is the last in this ranking. You can see that this growth is exponential. So if we are now in the so-called petaflop regime for these machines. But if one extrapolates this behavior to in the future, you can see that we reach the exaflop barrier here by sometime next year or in 2019. And I wanted to show this slide because, first of all, to realize the power that we have at our disposal, but also to make you aware of the fact that using this machine is very difficult, it's very complicated. And to run successfully large-scale cosmological simulation, one needs to know not only the physics of galaxy formation, but also numerics and some elements of computer science, in such a way that one can use efficiently those machines.
Is that flattening trend, the fact that clock speeds are no longer increasing on chips? Do you know?
It has been said that the main problem to reach exaflop is power consumption. So if you extrapolate, is it possible to do exaflop machine with the chips that we have now, but then you need a small nuclear power plant to power the machine. So that's now what they are working on, to reduce the power consumption per floating point operation. And that's the main technological challenge that have to be overcome. I also want to make the point that astrophysics has been one of the main drivers for this increase in computing power. So most of this, the installation of this powerful machine has been possible because we needed computing power to run those simulations. And to make this point, I'm going to show you the allocation time in one of these supercomputers that is located in Germany. This is a bit outdated. This is a couple of years ago. But nevertheless, you can see that of all the computing time that has been awarded on this machine, almost 1/3 was used for astrophysical applications. And so astrophysics and especially cosmological simulation have been one of the main drivers behind this computing power increase. And here is just a table of the top 5 supercomputers in the world nowadays. And this is to make the point that now this machine have a number of cores that range between 100,000 to tens of millions CPUs. And so you can imagine that it's very difficult to use the full potentiality of this machine. Also because the simulation I'm going to talk you about, which are state-of-the-art, don't use more than 1,000 to tens of thousands of cores. So we use just a fraction of the machine. And the point here is that if we want to make more progress in this field, we also have to be able to make a better use of the hardware that we have available. And even more so, if you think that in a couple of years we will have even more powerful supercomputer.
That's because you don't scale past 10,000?
That's because we don't scale past 10,000. Yes, it's very difficult to scale past 10,000, especially in some of the applications that I'll show you afterwards. Nevertheless, even if we don't scale so well, we have done quite a good job. So you can repeat this Moore's law for supercomputer by replacing the performance of supercomputer with number of resolution elements that are now evolved in cosmological simulations, again as a function of time. And you can see that also here the increase has been exponential. And this tells you about the close link between the installed computing power and the capabilities of cosmological simulation that we can run. Just to give you some numbers about the state of the art of the simulation, in cosmological boxes, I'm going to talk a little bit more about this subdivision of cosmological simulation later on in the talk, but it's now customary to evolve 10 of billions of resolution elements and to achieve a force resolution of about a kiloparsec. And while if you focus on the formation of a single object, you evolve less resolution element, but you can reach a higher force resolution. And also, one has to bear in mind that running this simulation is a huge effort, both to develop the code, to develop the models, and also to run them, and it's a huge investment both in computing power and money, because it's not unusual for this type of simulation to consume more than 10 million CPU hours. Actually, with state-of-the-art simulation nowadays, we can burn 30 or 40 million CPU hours in a single calculation. And so it's a great investment, both of time and computing resources. Okay, so it is important for you to understand what are the physical ingredients that we put in cosmological simulation to understand the remaining part of the talk. So I'm briefly giving an overview about the physical processes that we are trying to simulate in this type of simulation. So the first ingredients that we put in this type of simulation is gravity. Gravity is the force that acts on large scale. It's actually the force that brings together this tiny seed for structural formation, as we infer from the cosmological microwave background, brings them together, puts them together, and assembles the large-scale structure and the dark matter halo within which galaxies are forming. And as far as gravity is concerned, we think that we have it under control if it is Newtonian. We have different methods for solving for gravity in cosmological simulation, but all solvers that have been tried are essentially in agreement with the result. Here I am presenting a code comparison project that has been done recently that shows the formation of a single dark matter halo. What you see color-coded here is dark matter column density at the end of the calculation. And the same initial condition have been involved by different codes that use different gravity solver. And you can see visually that the results are quite similar. So even if we use different techniques to evolve gravity, we are essentially in agreement on the outcome. One can see this more quantitatively if one looks at the density profile of the halo that I showed in the slide before. So here you have the dark matter density on this axis as a function of the distance from the center. And the different lines here are the different code that I presented so far. You can see that the agreement is quite good over a vast range of radial scales. Of course, if one looks into the detail, there are still variations in the prediction of this dark matter density profile of the order of 10%.
Can you go back one slide?
Yes.
Is this just gravity?
This is just gravity, yes.
So the satellite I see at 2 o'clock is in different locations.
It's in different locations. When I say that there is good agreement what can happen if you use different gravity solver, you can compute slightly different gravitational acceleration. And the time step on the simulation depends on the acceleration that you are computing. And so the orbits might be slightly different. If you take the same instant on time, the position of the satellites can be in a slightly different position.
How do you quantify that when you say things agree?
You quantify that by in a statistical sense, so you focus on this object, but suppose that you do a large-scale simulation and you repeat this large-scale simulation a lot of time. Actually, statistically, we find consistency between these results. Probably I was oversimplifying this here a little bit. It's just to give a visual impression that actually the central dark matter area looks similar for all codes. And in fact, you can see that there are also different in the central dark matter density distribution if you look closely. And there are, differences, as I said, of the order of 10%, but this is nothing compared when you try to simulate, for instance, hydrodynamics, and I'm going to present in the next slide.
But sorry, can you explain when you said that these are different solvers? Are these just different numerical methods for solving the same?
There are different numerical methods to solve for gravity. What you need to do to solve for gravity is compute the accelerations. And naive way would be compute the acceleration of each pair of particles, but this scales really badly. It's an n-square problem, so you wouldn't get too far with that. And then different techniques have been developed. It also depends whether you are using a code that is using particle or a code that is using a mesh even to compute the gravity. And there are different techniques tailored to different methods. And depending on which code you are using, you have to use different techniques. But yes, these are solvers basically that are used to compute efficiently gravitational acceleration in the simulation in such a way that it doesn't scale as the number of particles that you have squared. Otherwise, you wouldn't get too far. We have also to model hydrodynamics, as I was saying, and also here we have different techniques to model it. And there are two big families of technique. We have particle-based code like SPH, where the fluid is discretized as a collection of masses that are also interacting with pressure forces. Then we have mesh codes, where actually the volume of the simulation is partitioned in resolution element called cell, and then the fluid quantity are computed within those cells. And here the agreement, unfortunately, is not as good as for gravity, as you can see here. So here I'm presenting results with an SPH code, gadget. It's a very code that is widely used in the community. And this is a result for a mesh code, actually moving mesh code, which is called a repo, which is the code that I'm using in most of my calculation. And this is a standard test problem for this code, which is called the blob test. The blob test means that you have a cold spherical cloud, which is in pressure equilibrium with a less dense medium. But then this medium is moving from left to right with supersonic velocity, and this cloud should be crushed by Kelvin-Helmholtz instability in a very short period of time, a few times the Kelvin-Helmholtz time scale. That's what is happening in the grid code, but that's what is not happening in the SPH code. And here you can see that we don't have agreement to the 10% level. The agreement is much worse. And so one has to bear in mind that when we are modeling hydrodynamics, the results depend on the way you solve numerically your equation. I have to say that this comparison has prompted the SPH community to fix these problems, and actually this discrepancy is it's alleviated nowadays. So there are techniques that you can apply to the SPH code to get similar results to the mesh code, but one has to be aware of the fact that the result might depend also on the technique that you are using to model hydrodynamics. There are also a lot of key ingredients for galaxy formation simulation, but I want to briefly mention feedback processes, because these are very important processes in this type of calculation. And feedback processes are mostly used to keep under control star formation in this calculation. And there are basically two main types of feedback processes. One is supernova feedback, which is important for small mass galaxies. And with small mass galaxies, I mean galaxies that have a mass similar to the Milky Way or below. And this is a complicated topic that probably of which I can talk about hours, but just to make it simple, the main objective of implementing supernova feedback in this kind of calculation is to generate galactic scale outflows, as you can see in this nice image of a real galaxy, M82. This is the disk of the galaxy, and this is the material that is blown out from the disk by stellar feedback. This is an example that I've taken from my calculation, which follow the formation of this galaxy similar to the Milky Way in a cosmological simulation. This is the face-on projection of the gaseous disk. The blue gas, it's cold and star-forming gas, and the yellow gas is a more hot material. These are two edge-on projection. You can see the formation of the disk, and the arrows here gives you the direction of the velocity field of the gas. So you can see that the disk is supported by rotation, but you can also see that in the supernova feedback implementation that we use in this calculation, we can drive this bipolar outflow out of the disk. There are many successful implementations of this feedback. Each one is tailored to the specific code that people have used to perform the calculation. The other important family of feedback processes is AGN feedback. And AGN feedback acts on the scale of more massive galaxies, and it's needed in this kind of calculation to stop star formation altogether on these massive galaxies. So when I say massive galaxies, I mean galaxy massive, more massive than our own Milky Way. It is very difficult to have a successful implementation of this AGN feedback because it's more challenging to implement and also to test than stellar feedback, because this kind of feedback usually works in cluster of galaxies, which are the most massive structure in the universe, but they are very rare. And so, since they are very rare, one doesn't have a good statistic of this object in this kind of calculation to benchmark this feedback channel. So, putting all these ingredients together, I want to show you a movie taken from the illustrious simulation to make you understand visually how complex the problem of simulating galaxies is. And you can see that we are zooming in the dark matter distribution of the illustrious simulation. This is just the dark matter projection. So white color is denser dark matter. Here you can see the spatial scale of the simulation. And what we are going to do, we are going to zoom in into a single dark matter arrow that contains this galaxy. And movie goes on for quite a while, and at some point we will transition from the dark matter to the baryons, to the stellar light of the simulation. But the point here is the galaxy I was mentioning. The point I want to make here is that to actually get this beautiful galaxy at the center of the dark matter halo, we have to simulate all this huge range of scales. And also the feedback processes that I've mentioned before are acting on a scale that is smaller than this galaxy as a whole. So you can imagine that simulating all this array of scale is a very complex problem. And even with the fastest supercomputer that we have, we cannot simulate all this range of scale from the large scale, for instance, to an individual star within this galaxy. This would be impossible to simulate. And we have to resort to some ad hoc technique that are called subgrid technique, subgrid physics, subgrid baryonic physics. And many of the implementation of the feedback processes that I've mentioned before are done in this way. So it is very complicated to simulate galaxies, but nevertheless, in the recent past, we have made tremendous progress. And now I'm going to present you what is the state of the art in this cosmological simulation, also highlighting the major contribution that I've given to this research field. Let me start by defining two main types of cosmological simulation that are used in the communities. We have box simulation. In a box simulation, we simulate a portion of the universe. Usually this has a cubical shape. But this portion of the universe is to be large enough in order to allow us to make population studies and to have a reasonable statistic on the number of objects that we are simulating. The downside is that we have to sample this volume with constant density. I mean, at the beginning, the density is constant, but all the resolution elements have the same mass. And this limits the maximum resolution that we can achieve. Or we can forget about statistics and population studies and focus on the formation of a single object. And to do that, in the cosmological context, we use the so-called zoom-in simulations. We still simulate a large chunk of the universe, but actually we focus all of our computational effort in a tiny region around the object that we want to simulate, and we put most of our resolution element in this tiny region, and then we simulate the remainder of the box with the coarser resolution elements. Of course, we cannot study what happens in the low resolution region, which is put here just to have the large-scale gravitational field in the right place, but we can reach higher resolution and we can make detailed prediction for the formation of a single object and the properties of these single objects. As far as cosmological boxes are concerned, these two projects are now the state of the art. Both came out a couple of years ago. One is the Illustris project that's been run with this Coda repo that I was mentioning. And I was directly involved in this, actually not in running and analysis this large scale simulation, but in the development of the baryon physics module that was used in this computation. And I used this module to investigate the formation of a single Milky Way-like galaxies. I'm going to talk about this in a moment. And then there is the Eagle project that uses a custom-made version of an SPH code, which is Gadget. Both these simulations have been very successful, and the state of the art is to simulate boxes that have a size of 100 megaparsec and that can contain about 40,000 simulated galaxies, so we can make a population study. Just an highlight of what has been achieved in this simulation is that the morphological mix of galaxies is reproduced now. Galaxies come in two flavors. In the universe, there are elliptical or spheroidal galaxies that are elliptical or spheroidal in shape, and that host mostly an old stellar population and are not very actively star forming. And then there are these galaxies, like around Milky Way. Their morphology is that of a disk, where stars are actively forming. Then there is a third category, which is irregular galaxy that doesn't follow this division. But the main point here is that with this kind of calculation, we can now reproduce this morphological mix quite accurately. There are also other properties that can be reproduced that I'm not talking about because of time constraints. But these simulations have been really successful, although there are tensions with the observation that are being taken by the next generation of cosmological simulation. My work in the beginning...
When you say that you produce accurately, that means that you get the right ratios, roughly speaking?
We get the right ratios. We get the right ratio and approximately the right number per comoving volume as a function also of the stellar mass. This is not surprising because the right number is kind of given in the simulation, since when you use these baryonic feedback models, there are 3 parameters that have to be chosen, and the usual procedure to calibrate this model is to focus on a few key observable and get this right, so it's not a real prediction of the simulation. Then you tune the model, you calibrate the model, and then you look at all other kind of properties to see what are the prediction of the simulation and see where are to identify the area of tension with the observation, and maybe this tension are telling you what are the aspects of the model that you have to improve.
Just understand the state of the art. When you say you get the mix right, does that mean you get the right distribution of, disk thickness to width ratios, the right...
This, in this kind of simulation, is difficult to tell because of the resolution. So you have simulating this box, but then you have to take into account that the spatial resolution is a kiloparsec. It's not really the spatial resolution, it's the softening length that you use in the gravity calculation. And then you know that the thin disk of the Milky Way is 100 parsecs, so it's very difficult to resolve the dynamics of the thin disk of a Milky Way with this kind of simulation. As I said, here it's mostly statistical properties and population studies as a whole. There are also other problems with this simulation. For instance, the color distribution is not quite right. You get color dichotomy, so these elliptical galaxies are mostly red because they are not actively forming stars, and these have more of a blue color. There is a transition at some mass range, but in this particular simulation, this transition is not at the right mass spot. It's a too high mass. And this is a thing that has to be fixed, of course.
Which piece of physics is the most important to get the roughly right morphological?
The feedback that I was mentioning, this feedback mechanism, yes, both, because here you can control star formation. I talk about this a little bit in the next slide. So supernova feedback is really important if you want to get the disks. AGN feedback is very important if you want to have elliptical galaxies that don't have little or no star formation left. Otherwise, the gas, these are usually at the center of galaxy cluster where the gas is very dense and it will cool very rapidly, and you will have cooling flow and form a lot of stars if you don't prevent the gas from doing so.
It was specifically so for instance, ram pressure stripping and things like that aren't enough to help kind of...
This might help, but these are mostly environmental effects. Here I was taking galaxies that are at the center of their dark material, so they're going to be the main galaxy. You can also study the satellite population, but as I said, here the resolution allows you to study properly galaxies that have a stellar mass above 1 billion solar masses. So not the dwarf that you see around the Milky Way, but maybe the satellite galaxy that you see in a galaxy cluster can be modeled accurately. And to model smaller galaxies, you need to use this type of approach, this zoom-in approach, which is an area where I've given my main contribution. As I was mentioning before, you are focusing on the formation of a single object, and forming these galaxies in cosmological simulation was a nightmare in the lambda CDM model. And up to 5 years ago, for instance, you wouldn't see this beautiful disk coming out from a simulation, extended disk with a blue component, which means that they are star forming. And by the way, this is the first successful application of a repo to this calculation, and it's an effort that I've led. Now, these galaxies are usually formed in this kind of calculation, and as I said, this was a major problem, and it's mostly you're obtaining these nice results because of the stellar feedback prescription that have been put in the current generation of cosmological simulation that is more efficient at ejecting gas and keeping star formation under control. You can contrast the properties of these galaxies with a lot of observation because we have it for our own Milky Way and nearby galaxies. We have done this. I'm presenting some of the properties here. We don't need to go too much into the detail here, but we found a good agreement with the properties of the simulated galaxies and the observation of these galaxies in the nearby universe. One can study both the stellar distribution, the structural property of the galaxy, and also the gas content in the galaxy. This is a work that I've done very recently. I published this year, and here I'm mostly focusing on the neutral gas content. This is H1, neutral hydrogen, contained in this type of calculation. You can see that you can check the mass, you can trace the dynamics of this gas, and also cold gas is very important for star formation, can be used as a tracer of star formation. These are 3 different realizations of this galaxy. You can see that the morphology of this gas can differ, it can be more extended, all the panels have the same physical size, and then the disk, the H1 disk can be thinner or can be larger. Here we think that supernova feedback is at play, or you can have interaction with a companion that can at some point disturb the morphology of this disk. This hasn't happened here, but if you continue the calculation, you can see that there is a huge distortion on this disk due to the interaction with the companion.
So what is the column density roughly at like your lowest contour there?
The lowest contour, I played the lowest contour to 1 solar mass per square parsec, which is around 10 to the 20 centimeters square, 1.3 something, I don't remember exactly the number. And I've done so because usually observational is how you define the sizes of this disk. So you define the H1 radius or diameter as the average radius at which your column density reaches 1 solar mass per square parsec.
And are those disks like the main feeding mechanism for the stellar disk in terms of bringing it gas, or is gas also coming down in?
It's usually in the model that we have afterwards that are mostly perpendicular to the disk because this is the path of least resistance, and then there is a kind of fountain flow that is generated in the CGM of the galaxy, and usually then accretion comes preferentially at the edges of the disk. Yes. And that's why at late time you see that most of the star forming region are at the edge of the disk because the fresh gas that is needed for star formation actually rains down at the edge of the disk mostly.
What are the dots on these pictures?
The dot of this picture are pixels. So the dots here is the stellar light distribution. The color is tied to the age of the star. So if you see a blue dot, it's a young star. But by star here I mean we cannot solve the individual star in the galaxy. It's a single
You're not
star.
seeing stars on that scale.
No, it's a single stellar population. What we do, we take all the star particles that we have there. It's a sampling of the stars that are in the galaxy, and then we smooth with some projection technique to get this image. And and you have to get a smooth image, you have to smooth over some length, and the length depends on the neighboring particle that you have. And here on this scale, maybe you don't have any neighbor, and that's why you see the dot. The smoothing is not working fine. So it's an artifact of how we made the
But a
image.
dot is like 10 to the 5 stars, the star
Yes.
cluster.
Yes, the star cluster In this case, it's 10 to the 5. We have reached also 10 to the 4 with more high-resolution simulation. So it's not a single stellar particle, it's a single stellar population.
What's the smallest scale you can resolve?
In this simulation is about 100 parsec, the softening length. The size of individual gas cell can be much smaller depending on your density. You can reach down to 1 parsec, but I'm not quoting that 1 parsec is the resolution of this simulation because it wouldn't be honest on my side. This is the small scale that you can reach, but what you can resolve is more close to the softening length that you are using in the simulation, so about 100 parsec. Okay, so this is basically the state of the art of this simulation. They have been really successful. A lot of progress have been made in the recent past. But then, as you can see, we have more and more computing power upcoming, and then we can use this computing power to improve over the current generation of cosmological simulation. So the question is, how do we want to proceed? What we can do with this computing power that we have at our disposal? And there are two natural answers that comes out in the case of boxes and zoom-ins. In the case of boxes, you want to run larger box size so that you can increase your statistics. And this is important, especially for the rare object in the universe like galaxy cluster. While in the case of zoom-ins, what you want to do, you want to increase the resolution. So increase the number of resolution elements that you have in your high resolution region so that you can study the formation of these objects in more detail. So as far as the box are concerned, as I said, the main driver is to increase the statistics, so to simulate with the resolution that which is currently available, larger volumes of the universe. In such a way, we get a better sampling of the high mass end of the very massive galaxies and galaxy cluster. Those objects are rare, so if you increase your simulated volume, you get better statistics. And ideally, we want to simulate volume that are a factor of 10 or even more larger than the current state of the art, so that we can have about 1 million or more galaxies in our simulated box. There are, of course, numerical challenges that have to be overcome. First, as Joe was mentioning, is the scalability of the code. We now scale up to 10,000 core, but if we want to simulate larger volumes, suppose a factor 100 larger, we have to scale to a factor of 100 more cores. The other thing that is related with the code scalability is the memory consumption. You put more resolution element, you need more memory in your computer to simulate. And also, and this is a key point, is also the data management of this simulation, because we are approaching the level that this kind of calculation can produce petabytes of data. And so it's not easy to also analyze those kind of simulations. So for the illustrious simulation, I can say that a single snapshot is around 2 terabytes of data that one has to mine and one has to analyze in order to do the science that one wants to do. We have actually moved some steps in this direction, and what we have done is to run the illustrious TNG series. TNG stands for the next generation of cosmological simulation. And so this is a follow-up project of Illustris, but in this case we are not simulating a single box of 100 megaparsec of a side. We have also redone this because we have actually improved the galaxy formation physics model to solve some of the outstanding issues in the Illustris model. But also we simulate a smaller box at higher resolution and then a larger box at slightly lower resolution. There is always a trade-off between the volume that you can simulate and the maximum resolution that you can achieve. And this is particularly important, as I was saying, because this volume is 30 times larger than the original Illustris volume, and so you have a sample of around 300 galaxy cluster with a mass above 10 to the 14 solar masses. And also, another improvement in the realization of this calculation is now that this calculation includes magnetic fields that are evolved self-consistently in the ideal magneto-hydrodynamic case. Of course, this is not an effort that can be led by only one person, so I'm part of a big international collaboration that has run this simulation. These two boxes are finished, so they are redshift 0, and we are currently run the small box, which is the more challenging because of the higher resolution. And what I want to talk briefly about this series of simulation are results coming from this large box, and in particular results that concern magnetic fields. So I first have a movie that shows you what is the final distribution of the magnetic field in this calculation. So in this panel, I'm actually showing the temperature of the gas at redshift 0 in the box. In the other panel, I'm showing the intensity of the magnetic field, again at redshift 0. And you can see that there is a one-to-one correspondence. However, you have that both quantity trace the large scale structure of the universe. Here in this white bubble where there is the presence of hot gas, you can see feedback at work.
What's the size of the box?
The size of the box, this is a cutout of 100 megaparsec on a side.
And this is turbulent dynamo and outflows, or how are you generating the magnetic field?
So the magnetic field in the beginning, as I said, we are doing this in an ideal MHD case. So we have to start with a seed field, because if you start with a zero field in an ideal MHD, then the equations are perfectly happy to stay at zero magnetic field forever. And so we use a uniform magnetic seed field in one direction. I'm going to talk about this in more detail in my talk tomorrow. At very low intensity, we start with 10 to the minus 14 comoving Gauss at the beginning of the calculation, and then we let the simulation evolve, and this is the final distribution of the field. What is happening is that you are compressing the gas by creating the structure, and then since you are in the ideal MHD, the gas compression brings an amplification of the B field. And once you enter within the halo, the turbulence that is created by feedback processing and the assemble of the central structure actually drive a small-scale dynamo on the field and amplifies the magnetic field to a level of a micro-Gauss inside galaxies, 1 to 10 micro-Gauss inside galaxies. That's what's happening. And in fact, if you look at the magnetic field intensity on these void regions, what's happening is that you basically get the initial seed field density that you have put in the calculation. We of course checked not on this large scale calculation because they are very expensive to run, but on small scale calculations that the final properties of the magnetic field are not affected by the choice of the seed field that we put at the beginning. So you can vary the seed field by many order of magnitude. The only thing that is varying is the intensity of magnetic field that you recover in the low density region. In the high density region, you get more or less the same amplification, regardless of seed field.
Your turbulent model is not subgrid; it's all resolved.
That's what the MHD equation tells us.
Yeah, good.
And in fact, in the outskirts of this halo, the amplification is not so good because you are losing resolution, and then you don't get an amplification that is what the observation suggests.
So if you did a cross-correlation of the magnetic field with density, it would presumably be much better than with
yes,
temperature?
I had a plot. I didn't include this on this presentation, but I have a plot in tomorrow's talk. I'm going to show that plot. And there is a tight relation between the overdensity of the gas and the intensity of the magnetic field. And you can see what I've described in words, that in low density region, you follow the scaling expected from flux conservation. And then when you enter the halo regime, something happens and the relation tilts up by many orders of magnitude. You have a discrepancy of 4 to 5 orders of magnitude with respect to the expectation of flux conservation. There are many things that can be done once you have magnetic field in the simulation. Here I'm just presenting an application that we have investigated in the large box. So what I'm showing here is the most massive galaxy cluster in this box. And the background color here is the X-ray emission from the hot gas that is in this galaxy cluster. And the contours are extended radio emission that is synchrotron radiation originating from relativistic particles that are moving in the magnetic field that we are predicting in the simulation. So let this movie go. Now the cluster is spinning around the vertical axis. And what you can do with a relatively simple model for the relativistic electron in the intracluster medium of this cluster is to make mock observation for different instruments with the resolution of the instrument and the sensitivity on the instrument, and then you can study this radio emission in greater detail, and you can make also prediction for upcoming survey. If you're wondering what's this dot over here that is passing in front and back of the cluster, this is a substructure. It has high magnetic field, so in our model it would be detected in radio emission, in synchrotron emission, but then the temperature of the gas is too low for it went in X-ray, and so you don't see structure in X-ray. And so it's rotating around the cluster, so when it goes in front of the cluster or behind the cluster, you don't see it anymore. But that's just a subtraction.
What's your field strength in the cluster outskirts?
I should check this. I don't remember exactly. So in the center is around 10 microgauss. In the outskirts, depending at the virial radius, I think that you are a couple of order of magnitude above the seed field level, but then you drop very rapidly when you're going there. I should check the figure that I've given you might be only 10 times larger than the seed field strength, because the decline is very fast at the outskirts of the cluster. Because most of the amplification, of course, in the center is because it's there. There we have more resolution, and so the dynamo effects are more important in that region.
So the radio emission is from the cosmic ray electrons, or
it's from cosmic ray electrons, but in the simulation we are not following this consistently. So we have not put relativistic particle in this calculation. So we use a simple model to estimate the energy density distribution and the density distribution of such electron, and then from that model for electrons and the magnetic field that you have in the simulation, you can estimate the synchrotron emissivity and integrate it.
So the cosmic ray energy density is some correlating the density field, or
it's basically proportional to the magnetic field energy density in this model. Yes, and then you have to correct for the presence of protons. So you divide your energy between magnetic field and relativistic particle, and then you assume there is an electron to proton ratio. These are the two free parameters of the model. Then you choose that in a reasonable way to match scaling relation, and then you make this kind of prediction. And the parameters that we are getting are reasonable. And this is a very simple model, so it can be improved in many ways. And actually, if I have time, I want to get to cosmic rays in these simulations. So the other thing that we can do with more computing power is to increase the resolution of zoom-in simulation, perhaps to reach the goal of 1 parsec, so that we can resolve structure in the interstellar medium of those galaxies. And this will allow us to explore many more physical processes. Again, there are challenges that must be overcome. Again, the scalability of the code might be an issue, because most of the action is occurring in this volume, and it's not easy to partition this volume and assign the load to each processor. Then you need to implement this new physics that you want to study, and this is, again, taking a lot of development time. Then there is the issue of the convergence, which is not well defined in this type of calculation, and it depends actually on how you implement your baryonic physics. I've been also active in this field, and I'm going to show you some preliminary results of this Auriga project. The Auriga project is basically the continuation of the zoom-in Milky Way project that I started while I was a postdoc in Heidelberg. And there are 3 major improvements. First of all, we are including, again, magnetic fields. And then, instead of having a handful of galaxies, we had 8 galaxies before, now we have 30. These are all the 30 galaxies that we are forming in this simulation. You can see that we form extended and star-forming disks again.
Is this the same halo mass?
It's a range of halo mass, but it's targeted to be around 10 to the 12 solar masses. It goes, if I remember right, from 0.7 or 0.8 times 10 to the 12 up to 2 times 10 to the 12. And even more important...
Cherry picked to be isolated, or is it just any halo randomly?
There is some isolation criterion in a similar way to what has been done for the Aquarius runs. And this isolation criterion is not very strong, but ensures that actually in many of the cases you produce a nice disk. For instance, in this case you see that the isolation criterion didn't work very well, because you have a major merger occurring at redshift 0. And more importantly, these calculations are done at a resolution that is 8 times better than the calculation I showed in the beginning of the talk. And there is more. We have targeted some of these halos, and we have run them at a resolution level that is even better than our fiducial level with Auriga, and it means that we have gained another factor of 8 in mass resolution. This is one of the most resolved simulation of this galaxy performed so far. We have also another project that is trying to extend it to gain another resolution level, so another factor of 8 in mass. This is extremely challenging. We have started this, but it's very challenging from the numerical point of view. The point I want to make here is that you visually compare those two images. You can see that the higher resolution is bringing out more finer detail, and you can start seeing the spiral structure of this galaxy. And this can allow us in the future, either at this resolution level, actually we haven't started the analysis of this level yet, or with the next level that I was telling you about, to actually study the dynamics of spiral arm and the stellar dynamics within this system. So in the last, I guess, 5 minutes that I have available, I want to briefly touch upon how we can increase the physical fidelity of the simulation. So with higher resolution, we can implement also additional physical processes that have been poorly explored in the current or ongoing generation of cosmological simulations. And I take as an example 3 different physical processes. The first one is thermal conduction, which might be important in high temperature plasma, such as the plasma that is filling galaxy clusters. The problem with thermal conduction is that it's diffusive transport of heat mediated by free electrons. But the plasma in galaxy cluster is permeated by magnetic fields, and since electrons are charged particles, they are bound to follow the magnetic field line. So this process is anisotropic. And in a grid code, and especially in a grid code like a repo, it's a nightmare to implement. Nevertheless, we have done this. I've collaborated to another MIT postdoc that has implemented this physical process in the simulations. This is a test, numerical test that we have made, in which we have a patch of hot gas, and which is surrounded by cold gas, and the heat should diffuse, but then there is a toroidal magnetic field here, so the heat can only diffuse along the magnetic field line, and there should be little or no conduction perpendicularly to the field line. This is to show the ability of the code of handle this very particular situation. But then we have applied this to the case of galaxy cluster simulation, and in particular we have checked what is the distribution of the abundance of heavy elements, the metallicity profile, as a function of the distance from the center to the cluster. In the case where we don't include thermal conduction, which is this blue line, and in the case where we include thermal conduction, which is the red line, and the yellow and the black line are observational constraint, and you can see that if we include thermal conduction, we are matching the observational constraint much better than if we don't include this process, where there is a pile-up of heavy elements at the center of the cluster. And this is because the thermal conduction can spread the energy of the AGN feedback on a much larger scale, and this promotes the mixing of metals. So it removes this pile-up of heavy elements here and transports it in the outskirts of the cluster.
The field geometry is just whatever you get from structure formation?
Yes, the field geometry is followed consistently in the same way of the simulation that I've shown you before. Only on the top there is thermal conduction operating in this case, in this fully anisotropic case.
How much is it different if you are not including the magnetic field, the metallicity?
Well, then the thermal conduction is isotropic. It's simple to implement, but it's also much more effective.
So the metallicity gradient,
I'm not sure whether Raoul has run this without magnetic field or by assuming that the thermal conduction is isotropic. What I can expect is that the effect is even more pronounced, but then all these things are related together. It's not that you have magnetic field and only thermal conduction. These gases are accreting onto the central black hole, and maybe you can quench this accretion, or you can increase this accretion, then the black hole will output more feedback. I don't have an answer for that, unless I see what happens exactly in the simulations, because all these things are tightly coupled together. And so if you change one aspect, oftentimes the results that you expect is not what comes out from the simulation, because of some coupling between these different physical processes. So another aspect on which we are working on are the inclusion of cosmic rays in these calculations. And again, cosmic rays are relativistic particles. It would be needed to model this ab initio, to model the synchrotron emission I was describing in galaxy clusters. And again, these are kind of a nightmare to implement, first of all, because they are relativistic, and second, because again, they are charged particles, and if you have magnetic fields, they can diffuse over magnetic field lines. So you have many of the problems that you have to implement thermal conduction also for cosmic rays. But nevertheless, we are working on an implementation of cosmic rays, and we have already run some idealized simulation of these galaxies to see if cosmic rays can have an impact in launching outflows outside the disk. So this is a portion of the disk similar to the Milky Way with the gas column density of with values that are consistent with what you can find at the solar radius. And in this run, we didn't include cosmic rays; we just include supernova explosions. You see that something happens to the disk, and some of the material is driven to 1 kiloparsec away from the disk, but nothing much happens. Then we added cosmic rays, so part of the supernova energy was used to accelerate cosmic rays. But we didn't include all the processes that these cosmic rays are based to. So in this case, we just advect the cosmic rays with the fluid. And you see that the outcome is quite different. The scale height of the disk is much larger, but if you see at the material that is driven out, it reaches more or less the same height. And then you include cosmic ray diffusion, and again the result is even more different, both for what concerns the properties of the central disk and of the properties of the outflows. You can see that the powerful outflows is actually driven in this case. We are still working on that, and this it appears to be a hot topic, so there are going to be more and more results coming in the next years. And finally, another project I'm doing is this more exotic models, if you want, of dark matter. As I mentioned at the beginning of the talk, in our simulation, we allow dark matter to interact only gravitationally. In this model, actually, dark matter feels, again, the gravitational pull, but also it has a cross-section which is non-zero for scattering. And this is to solve some small-scale tension that lambda CDM has, especially in pure cold dark matter simulation with the observation, especially for what concerns the abundance of substructure. In this work, one has the result from a halo coming from pure lambda CDM and then 3 different incarnations of this model. The point that I want to make here is that you can visually see that the number of substructure is reduced in this calculation, but actually we are not simulating baryonic physics here, and so we don't have a galaxy sitting at the bottom of this dark matter halo. And we are currently running simulations that are including this model of self-interacting dark matter and baryon physics, and they are still running, so I don't know the results yet, but the hope is that we can form also realistic galaxies in this kind of model, and this can alleviate some other tension that are present on small scales. For
varying the cross-section or the velocity dependence here?
Exactly, yes. Otherwise, if you go to high velocity, you might violate some constraint that you have for galaxy cluster. It means that your cross-section for interaction goes down as the velocity. I don't remember exactly what is the power law, the index of the power law. I think is the square of the velocity.
Is S-wave scattering? What's the presumption?
I don't remember exactly what is done in the model, but I think it should be an S-wave scattering. I need to check what is currently done. We have used this model to run this cosmological simulation, but actually this model has been developed by particle physicists. So they have given us the cross-section as a function of the velocity of the encounter, and we have implemented this in the simulation. I don't know too much the particle physics detail.
Neither do they.
Of the model, yes.
Careful, we people besides us in the audience.
This brings me to my summary. I won't be long, so I hope to have convinced you that cosmological simulation have made tremendous progress, and even though simulating galaxy formation is challenging both from a numerical point of view and from a physical point of view, but the increase in the computing power actually has allowed us to make a lot of progress. And also, for what concerns the future, it looks bright, but of course all this progress brings more challenges, especially if we want to have a simulation with more resolution and large simulated volumes. We have to implement a more faithful physical modeling, and this is a challenge in itself. And then the way to move forward is that we have to make detailed comparison to the observation, and the next generation of cosmological simulation will allow us to do that. And the hope is that by comparing to the observation, we can identify areas of tension of our calculation and improve our model to arrive at a better understanding of how the universe evolves. And then on a more lighter note, I found this very amusing. So this author has just computed what is the year at which the number of particles that will be simulated in cosmological simulation actually equals the number of dark matter particles that you can find on gigaparsec volume. depending on the mass of the dark matter particle candidate, because we don't know that. And actually, he made some choices, and by 2348 or 2386, we are getting there. So you just need to be a little bit patient, but then we will have unbelievably realistic simulations. Okay, thank you very much for your time.
Oh, sorry, Crystal, you have to go. Let's have you first. I'm sorry.
Go ahead, Lars.
Okay, Lars.
So what observations are you most looking forward to?
To make the comparison, you mean, to have constraining
When you're
power?
making a lot of predictions, what do you see as the observational?
So,
which thing just can't wait? What data can't you wait to see?
what data I can wait to see? So I would like to have more information about the medium around these galaxies, because there is a complex interplay of gas accretion and ejection, and this links very well to my work, also because these gaseous flow are actually setting the evolution of galaxies. So I'd like to have more information on that, especially on the density distribution, metallicity distribution. There is some work that is being done there, but simulations are not particularly well constrained. They are giving us great indications, but probably more precise observation in that sense would be really useful, so that we can constrain our model even better. Because if you have some room to accommodate the model, say you have an order of magnitude to accommodate your model, you are able to do this in this type of calculation, given that you have a lot of parameters that you can calibrate to reproduce a given observable. And then probably more information on galaxy cluster, although probably here it's the simulation side that is lagging behind, because simulating those objects is very complicated, especially if you include radiative cooling. Then you need to have a good AGN feedback model in order to stop star formation. Otherwise, cooling flow makes the gas so dense and you form so many stars that basically the simulation stops because of time step requirements. And also, all observations that have constraining power are welcomed. I'm looking forward actually to high redshift observation. Most of the comparison to the observation that are shown in this talk are at low redshift. And there is a reason for that. For instance, for the simulation of these galaxies, there is a reason, because the reason is basically 5 years ago we didn't have disks. So comparing the redshift zero property is the right thing to do, rotation curves and these things. But then at high redshift, this can be even more constraining, because maybe we get to realistic galaxy at redshift zero by the wrong path, and we have to check at each instant in time that we are basically doing the right thing.
You kind of suggested that the goal was making, a model that looks just like our actual universe.
Yes.
And I would argue that that's not really the goal, though, right? The goal is to derive physical insight about how our universe got to be the way it is.
Yes.
So if we take the disk specifically, because I know it literally took decades of work to get these realistic bulbs to disk ratios. I mean, I think I appreciate that one of the things that was learned was some of the numerical problems with SPH.
Yes.
But in terms of the physics of the galaxy assembly, can you summarize what's been learned there from this process?
So what we have learned there, so the main point was that most of the unsuccessful attempt was that the feedback was not efficient enough, especially stellar feedback. And by this, I don't mean that there wasn't enough energy in the feedback of this simulation, although there have been some strange experiments to get galaxy that crank up the feedback by the energy available for supernova by a factor of 10 or 100. And I think that the thing that we have learned is that the energy is enough, and then we have to couple this to the gas very efficiently, and that was the major problem there. And the major problem was there because these calculations, as I said, are pretty sophisticated, but the resolution is what it is. You cannot hope to solve the cooling radius of a supernova in this type of calculation, just because you don't have the resolution. And there has been a lot of work to understand what's going on, and I think that a major lesson that we have learned is that we have to connect the small-scale simulation to the large-scale simulation and have to talk one another. In the sense that with the small-scale simulation, you get the physical insight and what's happening on the small scale and what will emerge on the larger scale. And then you can put this on your cosmological simulation to have your cosmological context, which is, if you do an idealized simulation of this galaxy, I think there is a lot to learn there, but then you don't have all the, cosmic accretion, you don't have all the satellites that are orbiting around, you might not have the correct accretion rate on the galaxy, maybe the gas with which your outflows is interacting is not realistic because you have to put that by hand in an analyzed simulation. In a cosmological setup, you have this almost for free, not really for free because these are challenge simulation to run. So I think that the major lesson is really since we have to simulate this huge range of scale, is that small scale and large scale should talk and then find a point where to meet.
More questions, Jim?
I didn't understand clearly, maybe I missed it, how much information you get out about the statistics of the morphology, that is, ellipticals versus spirals versus hard spirals versus how many satellites per spiral, etc. Is that in the future, or is it in...
So as far as the satellites are concerned, if you are talking about statistics, that's probably in the future. Right. Because, as I said, there is always a trade-off between the volume that you want to simulate and the maximum resolution that you can achieve.
Yeah, so that's more resolution.
That's more resolution. But then if you want statistics, you also need larger volume. And this means that you increase your number of resolution elements by order of magnitude. By the morphological mix, what you can learn is how actually galaxies evolve from being star-forming to being not star-forming. And depending on how much time they spend in these two phases, you can learn what are the mechanisms that lead to the quenching of star formation. For instance, one of these is AGN feedback. And then if you have the time information about this transition, you can see what is the time scale for the AGN feedback to shut down star formation. And comparing this to the observation, galaxies are roughly divided in star-forming and non-star-forming galaxies. Then there is these Green Valley galaxies. They are not very much, so it means that this process has to be fast enough. So you can learn all these kind of things from just a morphological mix and statistical study. Even the color distribution can give you information about those things. Also, from statistical study, you can see if you have the right number of galaxies. In the past, the problem was that you were overproducing the number of galaxies. You were overproducing the mass, the stellar mass within galaxy, given the dark matter halo that you can actually infer from other techniques. There were all these problems. And actually, we have learned a lot by running this simulation and being successful in these respects.
Thanks.
So one last question, Matt.
Have you looked into maybe the topology of the seed field and how that might affect things? Because I can imagine having net magnetic flux in the box might change things.
This is a thing that we want to test. We haven't done that. No, we haven't done that. There is a reason, and the reason is that magnetic fields have these properties that they have to be solenoidal. So you also have to start the calculation with a solenoidal magnetic field. And to do this type of calculations, we actually have used the most simple configuration that was this homogeneous field. But of course, I haven't shown this, but I was mentioning that the field retains the strength on the void region, on the underdense region, and also retains the orientation because nothing much happens there. So you don't have this turbulent motion that derails the initial direction of the field. So yes, there is some residual dependence on this. It's not important as far as the formation of the central structure is concerned, but for instance, if you want to discriminate between different magnetogenesis scenarios, this is a thing that you have to study, because with the seed field that we have put in the simulation, what happens is that if you are in a void region, the field is coherent on the scale that you have put, that is the scale of the box. And of course, since this is sensitive to the seed field, this can probe different seed field, and if you try to constrain the magnetogenesis scenarios, you have to test all these seed field, different seed fields. And this is something that we want to do. Actually, we have implemented a seeding routine that uses power spectra for the seed field that are derived, for instance, by upper limits from Planck. And you can test all different power spectra that are actually calculated on the hypothesis that the seed field has different origin. And you can see if this changes the outcome of the simulation. We hope that, actually I don't know what to hope. Sometimes you hope that this changes because then you can constrain things. Sometimes you hope that this doesn't change, so it doesn't really matter what you put in. So I'm a little bit, uncertain of what to hope for, but that's for sure a thing that we have to explore in the next calculations, yes.
Okay, let's thank Federico again.